We have come to everyone's favorite part of precalculus, namely trigonometric identities. This is a concept that you're actually already familiar with in other realms of math. For example, x plus x equals 2x. That's true for all values of x. Here's a slightly more complicated identity. It's a quadratic that has been factored. X squared plus x minus 2 is equal to x plus 2 times x minus 1. And this is true for every single value of x. We can prove that through factoring or distributing. But I'd just like to drive home the point of what an identity really is. I'm going to provide you some numerical evidence that this expression and this expression are actually the same thing. And to do that, we're going to plug in a few different values of x and see what we get. If x equals negative 2, and I plug it into this trinomial, I get 4 minus 2 minus 2, which is 0. However, if I plug in negative 2 into the factored form, I get negative 2 plus 2, which is 0, times I don't care, because 0 times anything equals 0. So we see that the two expressions are equal to each other when x equals negative 2. Okay? If we try the same thing with negative 1 for our x value, we get 1 minus 1 minus 2, which is negative 2. Down here we get 1 times negative 2. And lo and behold, we get the same output whether we plug that negative 1 into the first expression or the second expression. So this pattern will continue. We try x equals 0. We're going to get negative 2 for the top, and we're going to get negative 2 for the bottom. We plug in 1 on the top, and we get 0. And we plug in 1 in the bottom, and we get 0. And finally, if we plug in 2 in the top, we get 4 plus 2 minus 2 is 4. And on the bottom, we get 4 times 1, which is 4. So this is some numerical evidence that it doesn't matter what x value you use to evaluate these expressions, you will always get the same output for the given input, which tells us that this is an identity. That's what an identity is. All right. Yeah, so as I mentioned before, we can prove that this is an identity using known algebra techniques, right? X times x is x squared. X times negative 1 is negative x. 2 times x is 2x. And 2 times negative 1 is negative 2. Combining like terms gives us, no surprise there, the original quadratic expression. All right, so that's some verification that it is in fact true for all values of x. Now we're going to move on to some trigonometric identities. There are a bunch of them, but the good news is you already know a lot of them. You know all of these fundamental trigonometric identities. For example, the reciprocal identities. If I ask you what is the reciprocal of the sine of theta, you should remember that that is the cosecant of theta. Oops, they're not equal to each other, but they're equal to the reciprocal of the other. So 1 over the cosecant of theta, right? Because sine of theta is defined to be y over r, and cosecant of theta is defined to be r over y. And that would mean that the reciprocal of cosecant is, you guessed it, sine. And the same thing can be said about cosine and secant. They are reciprocals of one another. Yikes. 1 over secant of theta is the same thing as the cosine of theta. 1 over cosine of theta is the same thing as the secant of theta. And finally, 1 over tangent of theta, or 1 over cotangent of theta, is the same thing as tangent of theta. And 1 over the tangent of theta is the same thing as the cotangent of theta. So, I don't know what happened over here. My sine of theta just jumped. Gotta love OneNote. The other ones that we already know are the quotient identities. Namely, we can write the tangent of theta as a quotient of two known trig functions. And that would be sine of theta over cosine of theta. We've seen that before. Remember that the sine of theta is y over r, and the cosine of theta is x over r. And when you divide fractions, you're multiplying by the reciprocal, so the r's cancel out, and we get y over x, and that is the same thing as the tangent of theta. So that's a pretty easy one. And then likewise, if we know the reciprocals, then we know that the cotangent is going to be the same thing as the cosine divided by the sine. All right, so these are some fundamental ones. You're already familiar with them, but let's make sure that we explicitly talk about them now because we need to know them going forward. So how do we use these in a problem? Well, let's take a look at this. If I know that the secant of alpha is 12 over 5, and I'm interested in figuring out what the cosine of alpha is, well, I know that the cosine of alpha is the same thing as 1 over the secant of alpha, right? Because that's an identity that we have up here. But I know that the secant of alpha is 12 over 5, so this is 1 over 12 fifths, which is the same thing as 5 twelfths. So all we really have to do is take the reciprocal of one of the values and we get the other value. Same deal over here. The sine of beta is given as negative 1/4. Cosecant of beta, well, cosecant of beta is the same thing as 1 over the sine of beta. But if I know that the sine of beta is the same thing as negative 1/4, then I can just say, oh, 1 divided by negative 1/4 is negative 4, and that's going to be our cosecant of beta. To up the level of difficulty a bit, we're given two different values here. Neither one of them is the reciprocal of the sine. However, I do know that the secant of theta is the same thing as the 1 over the cosine of theta. So if I know that the secant of theta is negative 5 root 2, then I know that the cosine of theta equals the reciprocal of that value, or negative 1 over 5 root 2. All right, well, how does that help? Well, we also know that the tangent of theta is equal to the sine of theta divided by the cosine of theta. And we know what the tangent of theta is. It's 7. I don't know what the sine of theta is. That's what I'm asked to find. But I do know what the cosine of theta is. It's negative 1 over 5 root 2. Okay? So this is the same thing as negative 5 root 2 times the sine of theta, right? Dividing by a fraction is the same thing as multiplying by its reciprocal. So if I'm looking for the sine of theta, I'm simply going to divide both sides by negative 5 root 2. So I'm going to get 7 on the top and negative 5 root 2 on the bottom. If you feel like rationalizing, great. If you want to leave it like that, that's fine too. We're going to try a similar problem over here. Let's see, we know that the cosecant of, this is the Greek letter phi, is going to be the reciprocal of the sine of phi. So we know that the sine of phi is 2 over 5 root 5. And we know that the cosine of phi is 11 over 5 root 5. And we know that the cotangent is the cosine of phi over the sine of phi. And we know what both of those values are because we just found them over here. Cosine goes on the top, so that'll be 11 over 5 root 5. And sine of phi is 2 over 5 root 5. And we can change that to a multiplication problem. By dividing by a fraction is the same as multiplying by a reciprocal. And the 5 root 5s cancel out, so we end up with 11 over 2. Deceptively simple answer compared to the scary looking beginning of this problem.